All right, hello and welcome to the recorded lecture for Lecture 7, where we're going to talk about the increasingly extensive use of collider physics to make discoveries in elementary particle physics, which is a transition which is very much going on in the era of the mid to late 1970s, which is where we will pick up the story today. So last time we talked about the so-called November Revolution, which saw particle colliders taking center stage. There's two areas in which this further progress along this direction can be seen. The first is the discovery of the tau lepton in experiments both at SLAC and at DAISY, sort of following right after the discovery of the charm quark. And around the same time, dramatic confirmation of the picture of hadrons that we had discussed a few lectures ago. This Feynman-Bjorken picture inspired by the results of deep inelastic scattering experiments, which led to the conclusion that hadrons like the proton are not themselves elementary particles, but instead the scaling behavior that you see in high momentum electron probes of these particles indicates that there is a hard constituent, which Feynman called the parton, which we now identify with the quarks and with the quarks inside the proton. And what we'll see today is the dramatic confirmation of that picture by making a more direct measurement of 3 jet events in E plus E minus collisions. We'll get to that a little bit later, but first let's start with the tau. So along the same line of research, these deep inelastic scattering experiments at Stanford that revealed the partons inside the proton, a number of scientists at SLAC, including Martin Pearl, who was one of the drivers of this line of research, became curious about what differences there might be between deep inelastic scattering experiments done with electrons and deep inelastic scattering experiments done with muons. So at the time, this is a figure from Pearl's paper in 1971, where he's explaining why one might be interested in this line of research. He says, imagine that the muon may have some new interaction with the constituents of the proton, which the electron does not possess. Right. The question that he's motivated by is the muon simply a heavier copy of the electron, or is there more to it than that? So he speculated that maybe the muon might have interactions with hadrons that the electron does not. And so people know how to make muon beams. We talked about that a few lectures ago. Basically, you can slam particles into a target that will produce a bunch of stuff, including some particles which decay in flight, yielding muons. By choosing the correct magnetic field and having the right amount of absorber, et cetera, you can create a beam of muons with the desired momentum range, and then you can fire this beam into a target. So the concept of doing these experiments is relatively straightforward, but this effort to put a limit on new interactions that the muon has with the proton is ultimately unsuccessful. And the main reason for that is because of large systematic uncertainties on these experiments related to differences in the experimental techniques for working with electron beams versus muon beams. Basically, the strategy to produce an electron beam is more straightforward. There's less pollution with other types of particles, et cetera. And so they were ultimately unsuccessful in being able to really quantitatively make a statement about the differences between electron interactions with protons and muon interactions with protons. So their mind went to other experiments that you might do in order to try to further explore the relationship between the electron and the muon. One idea was that you might actually try to learn something about this difference by looking for yet another type of heavy lepton, a new type of heavy lepton, and its properties might help to clarify the relationship between the different families of leptons. So with only two data points, the electron and muon, some trends that you could imagine might not extend to a third heavy lepton, others might. And so the idea of searching for new heavy leptons is a attractive one if you're trying to understand the nature of the different generations of matter. There were a number of ideas on the market at this time, circa 1970, for what those new lepton types might be. There's an idea called sequential leptons, which turns out to be the idea with the closest relation to the real nature of the tau we now know. It's even possible still that there are further generations, for example, a fourth generation of matter particle, although there's some constraints on what the masses of those particles could be. We'll talk more about that a little bit later on. But there were also other ideas on the market. One such idea was excited leptons. So if heavy leptons like the muon are actually excited versions of the electron, imagine that the electron is not a fundamental particle, but some kind of bound state, then one might imagine that the muon is like a second, is like an excited state of this thing, and that further heavy leptons would match this pattern. If this is the case, then one can hypothesize that you will see decays of the form mu to E gamma, for example. So if the muon is an excited state of the electron, has a finite mass splitting, that means after some time there should be a probability for it to decay back down to the ground state, which can do by emitting another particle, most likely a photon. Actually, searches like this are still of interest. We are still building experiments to evaluate if there might be some very tiny branching ratio for the muon to decay to electrons in this way. And this is a process which is simple, quote unquote, simple to observe, but is a very sensitive probe of possible physics beyond the standard model. So it's still a reaction of interest. There are also these ideas called paraleptons or ortholeptons. And these were basically names for attempts to generate different symmetry grouping of the two known flavors, the electron, the muon, and their associated neutrinos. So there's different kinds of symmetry groupings you can imagine. For example, the positively charged leptons might have a +1 of some new quantum number, and their antiparticles minus. Those were called paraleptons or ortholeptons, where the positive quantum number is carried by the negatively charged version rather than the positively charged version. And there are various symmetry schemes proposed, some of which predicted the emergence of new charged leptons or new neutrinos or both, and also possibly new interactions of the leptons, which had not yet been observed. Finally, some people thought that new heavy leptons might be long-lived or even stable, which we now know not to be the case. The muon decays back to the electron through emission of a muon antineutrino and an electron antineutrino. But you could imagine a case, for example, in the case of sequential leptons, where the third generation family had a very massive neutrino, or where it had a small mass splitting with, for example, the charged lepton, such that this decay would happen with some lifetime. Or it could be stable in the case where the neutrino of the third generation would be even more massive than the charged lepton of the third generation, and thus that charged lepton would have nothing it could decay to. So the experiment to look for a stable charged lepton will look rather different than the one that I'm about to describe. And in fact, this is also something which people have still done experiments on in the intervening years, looking for new stable leptons. So far, we haven't found any. But it was the heavy sequential lepton, which seemed like the most straightforward extension of what we know about the relationship between the electron and the muon. And so it was reasonable to propose an experiment which could go and look for this heavy sequential lepton. Here, Pearl uses the notation mu prime for the 3rd generation sequential lepton, mu double prime for the 4th generation sequential lepton, etc. And then these sequential leptons are imagined to have their corresponding flavors of neutrinos using the same notation. And he says, further suppose that each charged lepton and its associated neutrino possess a unique lepton number property, which is different from the lepton number possessed by every other charged lepton neutrino pair, and that these lepton numbers are separately conserved in the strong electromagnetic and weak interactions. Therefore, there would be no decay of mu prime to mu gamma or mu prime to E gamma. And therefore, the heavy sequential leptons would not be able to decay electromagnetically. The only option available to them would be to decay as the muon does through the weak interaction in these fully leptonic modes, which again are exact analogies for the decay of the muon to the electron through emission of 2 neutrino species. However, the muon is forced to decay this way because there are no lighter states available for it to decay to other than to the electron. But if the new heavy lepton is heavy enough, let's imagine it's a few GeV in mass, there's actually a rich spectroscopy of hadrons between the muon mass and this new heavy sequential lepton mass that would enable it to have decays of the form pictured on line 11 here. You could imagine that mu prime could decay to the sequential lepton neutrino plus 2 or more hadrons. And so that opens up another possibility for how you might search for this thing, not only looking for decays to leptons plus missing energy, but also to hadrons plus missing energy. There were a number of ideas on the market for how one might realize this experiment. So people thought of generating particle beams of various species and looking for evidence of decays in flight that match these hypotheses. Production by electron-positron annihilation is an attractive possibility. It's something which the technology to do is coming into use. First attempts to build a E plus E minus collider are happening sort of in the late 50s and through the 60s. And as we saw last time, it's eventually realized in a useful energy range by the SPEAR storage ring at SLAC. There were other storage rings around at the time, which just were unfortunate to have too low center of mass energy to have any new states accessible. But you could also imagine other things, photo production. So production through exchange of a high energy photon. You might try building a proton-proton collider. People will do this pretty soon, and we'll talk more in the next few lectures about what things are discovered once they start doing that. You might also do experiments like lepton-proton scattering, lepton-bremsstrahlung, or neutrino-nucleon inelastic scattering. Depending on exactly what the nature of this new heavy lepton would determine which of these search strategies are most likely to work. And the available technology determines which of them is the most attractive. So of these methods, the one that is probably the most general is the production by electron-positron annihilation. If we imagine that this lepton is charged, as the known leptons are, then it should interact electromagnetically, and therefore it should be easily produced in electron-positron annihilation. It's a relatively clean experiment, and you'll see phenomenology of the decays of this heavy lepton, which can then be quite striking. For at least the sequential case, and actually also for some of the other cases that we mentioned, electron-positron annihilation will pair produce the new lepton. And since this lepton can decay both to an electron plus neutrinos, but also to a muon plus neutrinos, that opens up the possibility of discovering it through a rather striking final state, where you have 2 charged leptons of opposite charge, but also different flavor, to E mu events plus missing energy. If the new heavy lepton is a point particle, which we thought that the electron and muon were due to the lack of, again, decays of the form mu to E gamma. Then the search can extend basically all the way up to the beam energy. This E mu final state is relatively clean and dramatic. There's not a lot of backgrounds that produce an electron and a muon plus missing energy. And particle ID of electrons versus muons is simpler than for other particles. In order to distinguish different species of hadrons, as we talked about a few lectures ago, you have to build these rather complex arrays of Cherenkov counters with different materials. But electrons can be easily detected in electromagnetic shower counters or electromagnetic calorimeter, as we would tend to call them today. And muons can simply be identified by their ability to penetrate through shielding that would stop all other particles. In particular, concrete shielding is cheap to produce and also a good structural element for building a detector. So it's pretty straightforward to imagine how you would build an experiment or a detector to look for this. These weak decays are very likely to exist just because we know that the muon can decay in this way. It's a good bet that the new heavy lepton should too. So taking all these factors into account, in 1971, Martin Pearl, who had been interested in this subject for some time now, suggested to use this spear ring, which we talked a little bit about last time at SLAC, to try and do this experiment, using the same Mark I detector that we briefly discussed last time for its role in the charm quark discovery. And in fact, the original proposal to the Department of Energy for the Mark I detector did include a chapter on heavy lepton searches using this technique, heavy lepton searches in the E mu plus missing energy final state. And this is something that we're going to see increasingly as we move closer and closer to the modern day. The increased cost and complexity of the detector systems, fueled in part by an increasing desire to instrument as much of the solid angle around the experiment as possible, tends to encourage this type of collaboration. So groups studying related but distinct physics topics are incentivized to band together to build the best possible detector for accomplishing their mutual goals in concert with one another. And soon you'll begin to see the proliferation of things like org charts, which carve up the available physics analyses into like different groups. Like in CMS, we have a group doing standard model physics and a group looking for Higgs physics in particular, groups looking at top physics in particular. And this sort of arrangement where people build and operate the detector together and then sort of carve up the available analysis space between them will become sort of the standard method of building these collaborations. The single purpose experiment does not die out completely, but the cost of these facilities really tips you in the direction of general purpose, or at least multi-purpose experiments when and wherever possible. Pearl had the idea to do this at Spear, but he's of course not the first person to have the idea to use E plus E minus collisions to search for new particles. This was attempted, probably the earliest example in 1960 by the so-called BCF group, that's Bologna, CERN, Frascati, led by Antonio Ziccici. There's a facility called Adone. This was an E plus E minus collider at Frascati outside of Rome in Italy. So he was a proponent of this idea, and when it eventually, the facility opened up later in that decade, they were able to exclude the presence of new heavy leptons below about 1.5 GeV. The reason for that is that the Adone center of mass energy was only 3 GeV. So if you're pair producing the particle, you can only pair produce it up to about 1.5 GeV. And even there, you see the cross section starts to fall off rather dramatically as you approach that limit. It's sort of tragic that this was so close and yet so far away from the energy that he would have needed to be successful. We now know that the tau mass is 1.776 GeV, so just to the right of the edge of this plot. So a minimum of 3.6 GeV in the center of mass is necessary to pair produce the tau And the cross section continues to rise with energy as you move beyond that. So just a little too early to have the available technology to do this properly. We mentioned last time the sort of energetic reasons why building a symmetric collider of this type is a cost-effective way of reaching higher energies than a fixed target collider with the same energy. Working in that sort of center of mass frame allows you to more fully use the energy of the beam that you do have and put all of that energy into the production of new particles rather than just a fraction of it. And so in the early 1970s, Burton Richter at SLAC, together with his co-workers there, fulfilled their ambition of constructing this E plus E minus ring spear. And the idea was that they would study E plus E minus annihilation in the 2.5 to 7.5 GeV center of mass energy region. However, as is often the case, the accelerator was to come online in a staged sort of way, meaning that while it could theoretically accelerate electrons and positrons up to a center of mass energy of 7.5 GeV, the maximum energy which they could attain with a really reasonable luminosity, which was useful for doing searches of the kind that we're talking about, that energy was limited to about 4.8 GeV in the early years. So this will lead, as we'll see, to a sort of extended period of slight confusion about the nature of the particle they're producing, because they're sitting sort of uncomfortably close to the production threshold, and they don't get to really copiously produce these particles in higher energy events until a few years later. This, again, is a picture of the Mark I detector at SLAC, which is one of the main sort of forerunners to the general purpose experiments like ATLAS and CMS that we still use today. Martin Pearl makes the following comment about the Mark I. He says, the use of a large solid angle particle tracking detector paired with a large solid angle particle identification system seems obvious now, but in 1970, it was not obvious. Again, the typical experiment in the sort of 50s and 60s was either an expansion chamber, which is usually serving as both the target and the imaging apparatus, and therefore, by definition, is going to be working in the fixed target mode, therefore not taking full advantage of the energy of the particle beams. And even where people were building electronic detectors to make use of like a fixed target experiment, because of the geometry there, the particles typically coming out strongly in the direction of the incoming beam, the typical mode of organization was to sort of build up facilities around the fixed target interaction point, each occupying their own slice of solid angle. So this enabled different groups with different hardware and different types of detectors to use the same beamline, which is efficient in that sense. But as experiments are pushed more and more to look at multi-particle correlations as a way of doing the physics, we'll see later on in this talk several examples which really could not have been done by detectors without large solid angle coverage. So it required a phase change in the social organization of physicists, bigger teams, bigger collaborations with more resources. It's expensive to instrument the whole solid angle. And especially when you're talking about things like these heavy lepton search, where the presence of a momentum imbalance is sort of one of the main features of the signal, it really behooves you to surround as much of the interaction point as possible with sensitive detector. This will be taken even a step further in the discovery of the W and Z particles, which we will talk about in a future lecture. But the idea here is that you have a cylindrical spark chamber inside of a solenoidal magnet, a 4.6 kilogauss field in that magnet. The magnet is then surrounded by time of flight counters for particle identification. We're talking now about particles typically in the momentum range of, say, a couple hundred MeV up to maybe 1 GeV. So the speed of these particles in the lab frame is still slow enough that one can relatively easily measure their arrival times in the time of flight counters and match them up with the track geometrically. Then there were shower counters surrounding that for photon and electron detection and identification, and by proportional counters embedded in the iron absorber slabs, which were used to do the muon identification. So it really looks in spirit very similar to something like CMS. And it was, while it's the culmination of some trends that were going on as far as building up bigger and bigger spectrometer systems around interaction points, I think it deserves credit for being the first of its kind. Last time we left off looking at this table. So once the spear detector turned on at this 4.8 GeV energy, which was the maximum energy that could produce a useful luminosity, you started to see almost immediately this striking class of events of exactly the type predicted by the sequential heavy lepton model. Events with an electron, a muon, and some energy imbalance, which you could see from the event displays. There's one on the next page. And that's exactly what this team was looking for. The main challenges in interpreting these results and trying to understand in a quantitative way if they really indicated the presence of a new particle were some instrumental effects. That should sound familiar to those of you who are doing analysis now. There's things that we still struggle with. First of all, how to measure the hadron misidentification rate into leptons. The experimenters knew that there was a significant probability that a hadron, for example, could punch through the shielding in front of the muon system. If you look at this picture on slide 10 here, the amount of sort of iron in the return yoke is only 20 centimeters. There's a good chance that like a charged pion, for example, will shower in 20 centimeters of iron, but it's not guaranteed. And so therefore, there's a pretty significant chance that your muons are not actually muons, but just pions, which happen to have punched through that 20 centimeters of iron. So one thing that the experimenters did to try to control this probability was to assume that any event with 3 or more prongs were actually hadronic events. There wasn't any idea that there was a reaction which could produce something like, 2 muons and a hadron in the same event. If you saw an event like that, there's a good probability that one or both of the muons that you saw are actually hadrons that were misidentified. Whereas they had a pretty small sample of 24 EMU events, they had a sample of 9,550 three-prong events. And by relating the number of events in that sample to the various categories here, you can basically make up a matrix of transfer factors with the different misidentification rates and solve for those different misidentification rates. You see here in this table 2 at the bottom that they can end up computing fake rates in the range of 13 to 30%, depending on the particle species and the momentum, which is enormous by our modern standards, but still good enough to show that these 24 EMU events could not be explained as chance misidentified HH events. Since there's only 13 HH events in the sample, you would need a significantly higher misidentification probability even than that in order to explain the number of observed EMU events. Another issue here is that by the modern standard, the solid angle coverage is not great. In particular, the E gamma identification and discrimination is not fantastic. It's covering only about half of the full solid angle of 4 pi, closer to 2 pi. And so the possibility that these events don't just have an EMU plus missing energy, but that there actually are other particles, maybe photons, in the final state, and they simply escape the detection, is a good possibility. That would also be an interesting class of events to observe, but it wouldn't have an obvious interpretation as a new heavy lepton. So they wanted to think about ways that they could control that possibility. And finally, the detector was made with the intention of surrounding the interaction point, but there were lots of cracks and gaps in between the detector elements needed, for example, for cables to move for cables to move the electrical signals out of the detector. In the case where you had these proportional chambers, you need to have some gas flowing, et cetera, et cetera. Still something we think a lot about. Part of the upgrade of CMS that we're doing for the HLHC involves putting new, more advanced, more power-hungry detectors into a space which was formerly occupied by a simpler kind of detector. I'm thinking, for example, of the NCAP calorimeter upgrade that I work on. And there too, like one of the major challenges is trying to fit all the needed services into a volume, which is sort of predefined for you by the detector design that you're inheriting. So this idea of thinking about clever ways to cover over cracks and gaps is something that's still very much a part of the art of doing experimental physics. One improvement that could be made would be to put additional muon chambers around the experiment, separated from the interaction point by much thicker absorber. So not just this 20 centimeters of iron. And so there was a idea called the muon tower, conceived of and built by a guy named Gary Feldman. We'll probably hear more about later on in the story. In 1975, this was added. It doesn't surround the whole experiment. It's just a tower sitting on top. But it greatly improves the reliability of the muon identification over, roughly a quarter of the angle of the experiment. And so you start to see events like the one in this display. These two thick concrete absorbers have then muon spark chambers interleaved with them, and you see the muon candidate coming out from the event. It's curving one direction in the magnetic field, then it crosses the return yoke, and it's moving in the other direction, curving in the other direction when it gets on the other side of that. And with this increased material, it becomes really much harder for a charged pion to punch through and fake a muon. There was a lot of skepticism in the community at first about this discovery. I mean, one of the things that gave people pause was that not only is this another new particle being discovered at the same experiment around the same time as the charm quark, but it's also very close in energy to the charm quark. So there was a lot of confusion sorting through like the excited states of the J psi. Could this be one? Could the J psi have exotic decays that made it look like a heavy lepton? And unlike the charm quark, there wasn't an obvious place for a third heavy lepton or for a new heavy lepton in the standard model. So we have this quark model, which comes from the deep inelastic scattering experiments. People knew about strange particles. And so the idea that there were two sort of quarks of the first generation up and down, and then this strange quark, which maybe logically belongs to a second generation, along with the muon, at least that's not how we think about it now, then you could very easily ask, well, then there should be another new heavy quark in this second generation. And the charm quark fit that bill perfectly. So it was somehow better motivated. The tau, a new heavy lepton opening up a third generation of matter, of which it would be the first indication, was a little bit more far-fetched. And so it took stronger evidence to convince people. It would have been nice, for example, to show that you saw the expected rates of the other decay modes that should happen. So if you can decay to E mu, and it seems that this particle has enough mass to also decay hadronically, then it would be comforting to observe the E hadron and mu hadron decays. So where it's pair produced and one of the pair decays hadronically and the other one still to a charged lepton. But we just got through talking about how the misidentification rates between electrons, muons, and hadrons were rather large. And so therefore, it was hard to manufacture a large enough sample to show definitive evidence of those combinations and not to fall back on the obvious interpretation that the E or mu in those events was just a misidentified hadron, HH or HHH events being much more common. Even in 1977, which is a couple of years after the initial discovery, here's what a popular science book on particle physics had to say. This guy Calder wrote a book called The Key to the Universe, where he writes in early 1977, Martin Pearl and his colleagues detected peculiar events occurring in SPEAR. From the scene of collision, an electron and a heavy electron, the well-known muon, carrying opposite electric charges, were ejected at the same moment without any other detectable particles coming out. No conventional process involving conventional particles could account for such events. The particle called U was the original name given to what we now call the tau, was grotesquely weighty for an electron. Theorists had been asking one another for many years why the muon, a heavy electron of 105 mass energy units, was 200 times heavier than the ordinary electron, 0.5 units. They had no answer to that. And the U particle was estimated to be 1,800 mass energy units, twice as heavy as a hydrogen atom. Doubts also overtook Stanford's heavy lepton, the U particle. There were suggestions, notably from the Doris experiments in Hamburg, that it was an illusion, perhaps a misinterpretation of the decay of charmed particles. At the time of writing, these doubts have not been resolved, and they illustrate again the difficulties and tensions of high-energy physics. A fair summary of the situation may be that there is no very compelling evidence so far for nature deploying more than 4 types of quarks and 4 members of the electron family. Well, he's forced to issue a second edition already later that year. So Calder 77b has changed to the particle U is grotesquely weighty for an electron. Theorists had been asking one another for many years why the muon, a heavy electron of 105 mass energy units, was 200 times heavier than the ordinary electron, 0.5 units. They had no answer even to that. And the U particle was estimated to be 1,800 mass energy units, twice as heavy as the hydrogen atom. Experiments with Doris and Hamburg confirmed the discovery. So there's a general uncertainty in these years that the tau was really a new heavy lepton, and we'll take independent confirmation from these experiments at Hamburg mentioned first in the negative, then later in the affirmative by Calder as confirmations to arrive. The Mark I team was not quite done yet. In addition to adding more muon spark chambers surrounding the experiment to further improve the muon identification or to further lower the misidentification rate, the team went on to add the so-called lead glass wall, sort of electromagnetic calorimeter that could aid the identification of electrons over a limited fraction of the solid angle. This also served to reduce the H to E misidentification rate. And with these 2 improvements, the muon tower, as well as additional spark chambers, and then this lead glass wall, the required EH and mu-H events, which were originally hard to confirm, started showing up in greater numbers. We mentioned a couple times already this Doris experiment at Hamburg at DAISY. So this was a project undertaken in 1968 at DAISY to build the first storage ring in Germany. It's about 300 meters long, called the double ring store, Doris for short. It's a bold decision at the time that it was taken because storage rings of this scale had never been attempted before. The technology was not very well understood, and nobody knew what exactly was there for this particle collider to study. However, it turned out they were very fortunate, right? I mean, having access to the same energy range as the SPEAR collider, they could sort of leap into this physics of the November Revolution near the beginning. And Doris actually continued to operate for a long time into the 21st century. As with many of these electron storage rings, its ultimate purpose was as a source of synchrotron radiation for material science, chemistry, biology, etc. So Doris was, again, an E plus E minus collider. It started up in 1974, so right at the opportune time to participate in the November Revolution and the subsequent discoveries. And Doris made a number of important discoveries during its lifetime, including major contributions to the spectroscopy of charmonium, so heavier CC bar states, which can decay back down to the lower energy states. And it's sort of helped to birth the field of flavor physics, heavy flavor physics. Here's one of the detectors at Doris called DASP. DASP, for double arm spectrometer. It also contributed to the understanding of those new charmonium states as well as of the new lepton. So here we see sort of history and the future colliding in a detector which is sort of having an identity crisis between a double arm spectrometer and a 4-pi detector. So you see this cross section of the experiment. It's very asymmetrical. The two arms of the magnetic spectrometer, which are on either side of the interaction point, give a good coverage with all kinds of particle identification capability, et cetera, but in a rather limited range. Then there's this central part of the detector, which makes a more honest attempt to surround the whole interaction point. But obviously, there's not much in the way of spectrometer capabilities above and below. Obviously, it's harder to build up into the air or down into the ground, which is kind of the reason that these spectrometers tended to grow out from the interaction point in the way that they did. But obviously, you're missing a lot of identification capability for any particles which are traveling in the vertical direction in this picture. But the trend is clear. The new generation of experiments coming online are going to look more and more like Mark I and less like Doris. The central detector is non-magnetic. It consists of an array of different things. You see the beam pipe here in the center. Then there's a number of shower counters surrounding. The top and bottom are instrumented with shower counters to be able to measure what particles are produced in the vertical direction that won't be measured anymore. Then there's a number of scintillator counters, multi-wire proportional chambers, et cetera, surrounding. But this is all without magnetic field. So any particle that doesn't make its way into the magnetic spectrometer arms, not pictured here at left and right of this picture, won't have a very good momentum measurement, but there's some amount of particle identification. And at the very least, they are able to veto events where significant numbers of particles are carrying energy away in the vertical direction. Nevertheless, their central spectrometer, despite being non-magnetic, and therefore not really much of a spectrometer, covers 75% of 4-pi. So that's actually better than Mark I in some ways. Here's a picture of what they found. This is the cross-section for E plus E minus annihilation into tau leptons as a function of the center of mass energy. DASP was able to scan up to a higher energy more quickly than SPEAR was, than Mark I was. And one thing they were able to show is that the threshold for production of this new state is different than one of the excited states of charmonium that lie sort of in the same range. So having this data tends to count against the hypothesis that what was observed was not a new heavy lepton at all, but rather just some kind of charmonium state. And they were also able to do a relatively precise mass measurement, getting 1787 plus 10 minus 18 MeV, which lies within their uncertainties of what we now accept to be the right value for the mass. And they're also able to show that the dependence that you observe here is consistent with the hypothesis of a spin 1/2 particle that is a fermion, which could be a lepton, as opposed to some other thing that has integer spin. So it took a few more years for people to fully study all the nearby resonances of hadrons and fully convince themselves that what we had here was really a new heavy lepton. But at this point, that process is well underway. So we're going to turn our attention now from the tau lepton to the other main topic of today's talk, which was the way that these collider experiments of the late 70s are able to confirm and in fact extend the detail of the parton picture, which was originally invoked in order to explain the results of deep inelastic scattering experiments. And people wouldn't have probably used the term QCD quite yet to describe these things, but that's where we're headed. So as a reminder, Feynman and Bjorken, among others, worked on interpreting the results of the deep inelastic scattering experiments at SLAC in terms of point-like constituent particles of the proton. It was already understood at the time that there was no evidence for these particles to be observed in reactions. Among other things, they were supposed to have a fractional electric charge, which no one had ever observed a particle consistent with having fractional electric charge. And the lack of any light states lying below the proton mass that could be identified as free quarks suggests that there's some physical principle which prevents them from appearing in isolation. The confinement of single quarks, so this phenomenon that they can't be observed except through their contributions to the properties of hadrons, is known as confinement. And the confinement of single quarks is explained by the introduction of a new quantum number, sort of whimsically given the name color. Color can take on 3 values, which we conventionally call red, blue, and green, and then their opposites. So only color singlet states can be observed directly, and we call those hadrons. You can have something which we call a meson, which is 2 quarks. In the color picture, then that would be like red, anti-red, or blue, anti-blue, or green, anti-green, in order for it to be a color singlet. Or it can be a baryon, and the way that it can be a color singlet as a baryon is to have red, green, blue, or anti-red, anti-green, anti-blue as its constituent quarks. So this idea that only color singlet states can be observed directly not only explains why we don't see free quarks flying around in our experiments, but also gives some predictions as to what should happen, for example, when we try to produce quark-anti-quark pairs by E plus E minus annihilation, which is what people are starting to try to do in these days. So let's return back to this picture. We already talked about this, studying this interaction and how it somewhat accidentally led to the discovery of charm. The idea here is that this process is a electron-positron annihilation into a virtual photon, and it results in the production of 2 fermions. Those fermions could be muons, for example, or they could be tau leptons, as we just saw, but they could also be quarks. Quarks are fermions, and everything matches at this vertex for them to be produced that way. In fact, you can do better than just saying that quarks should be produced. You can write down this ratio, which is the ratio of the cross-section for E plus E minus into quarks to the cross-section of E plus E minus into muons. So you can calculate this bottom process in quantum field theory. And for the top process, you can calculate it as well. And then you know the coupling strengths between the virtual photon and the quark should go as the square of their electric charge. Remember that in order for the charges of the quarks to add up to the charges of the mesons and baryons we have, they need to have these odd fractional charges, either minus 1/3 or plus 2/3. And so you can sum up the squares of those amplitudes. And then if you also add in this idea of color, the 3 colors being inspired by the fact that we see 2 quark states and 3 quark states, that would suggest that there's 3 colors, and therefore there should be an overall leading factor of 3 here. This coupling strength squared for each of the different quark types, and then multiplied by 3 for the 3 different colors that each of those quarks can take on. So a quantitative confirmation that the amplitude for this process matches the predictions of QCD would be a really good evidence that it was a correct theory. So the fact that this leading 3 is out here makes a huge difference. In the case where the 3 wasn't here, then this ratio would be 2/3. That is to say that the quark-anti-quark production cross-section should actually be less than that of the muon. But with this leading 3, it's a factor of 2 greater than for the muon. So that's a quantitative difference that you should be able to tell even with relatively limited statistics. Beyond that, the kinematics of both processes are the same, at least at this sort of tree level. So we can show that the angular distribution in both cases ought to be proportional to So the cross-section is a function of the angle theta, which is the angle between the incident and the outgoing directions. That the cross-section should go as 1 plus cos squared theta. So one piece of evidence for the quark model would be to measure this total cross-section of E plus E minus to hadrons. And again, that's exactly what people were trying to study at SPEAR with the Mark I detector when the sort of accidental discoveries of the charm and the tau were made. So the new resonances which were available at the SPEAR energies meant that this prediction failed in a spectacularly positive way. But later on, people went back and carefully measured what is the ratio in the regime before charm turns on, and it does match this prediction. So that's a pretty strong indirect confirmation of this quark picture. Another piece of evidence, of course, came from the deep inelastic scattering experiments that we discussed in lecture 5. The predicted scaling behavior of the Feynman-Bjorken parton picture is observed in the scaling of the scattering cross-section with Q squared, basically not falling off with Q squared, but remaining relatively flat. But this is also somewhat indirect evidence, and there were other ideas and interpretations on the market which were somewhat different, and you'd like to be able to discriminate between those possibilities. So by the late 1970s, people were really sort of itching to confirm this in a more direct way. And the idea was that they could use this phenomena, which we now call jets, in order to do that. So in E plus E minus reactions, the virtual photon couples to a quark-antiquark pair, as we saw on the last slide. However, if the energy in the center of mass is large enough, when we produce this quark-antiquark pair, they're not at rest in a bound state, but they're recoiling against each other with a large amount of momentum. The theory of confinement says that the binding energy between these two objects actually should increase with their separation. Put another way, that the force between them is constant at large distances rather than falling off as it does for gravity or electromagnetism. Thus, the potential energy of this arrangement, or the two quarks flying away from one another, grows, and it grows proportional to the separation between the quarks. And once the potential energy grows large enough, or put another way, the separation grows large enough, it becomes energetically favorable to pull a new quark-antiquark pair out of the vacuum. And these can then pair with their opposite from the original pair. And if there's still sufficient energy left over, this can result in multiple generations of new particles being produced, as is shown in this picture. So from an initial quark-antiquark pair, you end up with a large number of other hadrons, with that total number being related to the amount of energy in the original interaction. The more energy we give the quarks, the more particles we need to produce as the initial quark-antiquark pair flies away from one another. Not only that, on average, the spray of elementary particles which is produced will have a correlation with the energy and direction of the original quark-antiquark pair. So with collision energies sort of approaching 10 and soon tens of GeV, there's plenty of energy available to produce lots of hadrons, dozens or more of hadrons per event. And the directions of those hadrons should be correlated with the direction of the original partons. It's because they're flying away from one another that it's energetically favorable to produce those new particles. And so those new particles are going to be produced generally along the same axis as the original pair were moving away from one another. Typically, the particles in a jet have hundreds or so of MeV of momentum perpendicular to the jet axis. And that is picked up during this hadronization process, where the typical energy scale of hadrons is also a few hundred MeV, right? So the more energetic the jet, the more collimated the jet appears in the lab frame. But for very low energy jets, this hundreds of MeV of energy broadens the jet out in some cases so much that it's hard to really see it. But as you approach, 10, 20 or more GeV, they really become tightly collimated objects that are easier to see in your detector. So this had all been hypothesized already, even at the time that SPEAR was doing its studies in the mid-1970s. So they attempted to see the jets with the Mark I detector, but there were some difficulties. First of all, as we said, the center of mass energy there is maxing out at about 7.5 GeV. So that means that this typical hundreds of MeV of momentum picked up by the hadrons perpendicular to the jet axis makes the jets difficult to see just by looking at the directions of the tracks. What they did instead, and some of this work was done by Gail Hansen, among others, working on the Mark I experiment, is to define some event level variables that help you quantify how jet-like your event looks, if you will. And one of those variables is sphericity. So the idea behind sphericity is that you can find an axis in the event for which the sum of the squares of the particle momenta relative to that axis are minimized. If the process you're trying to study is this pair production of quarks in E plus E minus annihilation, and we think that the particles which result from the hadronization process are going to have their directions and energies correlated with the initial parton, then this axis along which the particles have a minimum of transverse momentum relative to it should correspond to the sort of axis along which the original QQ bar pair flew away. So you can sort of sum up all of the energies, all of the momenta perpendicular to that axis and divide by the sum of the squares of all the momentum in the event. If the spray of particles is totally isotropic or spherical, in the sense that there's no preferred direction to the event at all, then this sum should be close to 1, with the factor of 3 halves sort of serving to normalize over the number of available dimensions. But in the case of a jet-like event, then most of the particles are going to be traveling either together with the initial quark or together with the initial anti-quark, and they should lie more often than not with their momenta aligned along this preferred axis. And therefore, the perpendicular components as a fraction of the overall total will be much less. So a isotropic or spherical event will have a sphericity approaching 1, whereas a dijet type event or a jet-like event will have a sphericity close to 0. That is to say, the momenta perpendicular to this axis are much less than the momenta along the axis. Recall that the energy at SPEAR could be scanned over a range from about, I think, 2.5 up to 7.5 GeV. The considerations from the previous slide where we talked about the typical transverse momentum of the hadrons in the jets being at this fixed scale of a few hundred MeV, that indicates that the average sphericity should increase as the center of mass energy goes up. That is, the average sphericity should drop as the center of mass energy goes up. That is, that events become more jet-like because the initial parton energy starts to overwhelm the transverse spread, which is more or less fixed. And the second prediction is that if the jet-like events are really due to the outgoing quarks, then we should also see the jet axes going with this 1 plus co-squared theta dependence that we expect for spin 1/2 fermions, just as we do in the case of E to mu mu scattering. On the left here, figure 1 from the paper expressing evidence for jets at SPEAR. You see the prediction for the jet model of decreasing sphericity as the center of mass energy increases, the solid line here. And then the points with error bars are the observation. Clearly, there is a downward trend in the sphericity as the center of mass energy increases, just as the jet model would predict. The production angle is actually complicated a little bit by the fact that this is in general true for E plus E minus storage rings, is that actually as the energy increases, for reasons that I think we'll talk about later on when we get to the LEP collider, but for now, just take it as a given that as the energy in such a machine increases, so too does the typical amount of polarization. And by polarization here, I mean the alignment of the electron spin directions relative to each other and to the beam direction gets more pronounced as the energy increases. So one can compute the effect that this polarization has on the 1 plus cos theta distribution that we expect without this effect. So basically this cos squared theta term picks up this parameter alpha, which depends on the spin of the particle that you're producing. And then there's a second sine squared theta times cos 2 phi, where phi is an azimuthal asymmetry. That thing depends not only on alpha, but on the degree of polarization. So if you observe what the production cross-section per unit angle is, and then you can fit this term to it and try to extract the alpha value given the polarization that you have at that energy. And if you see an alpha value closer to 1, that means the particle is more spin 1/2 like. If you see a alpha value which is closer to -1, that means the particle is more spin 0 like. Well, here's the distribution that they observed at top at 6.2 GeV in the center of mass, where the polarization is having relatively less of an effect. And at the bottom, the center of mass energy of 7.4 near their maximum, where they see the maximum amount of polarization. They extract this alpha term and find it to be 0.78 plus or minus 0.12. It's much closer to alpha of 1 than alpha of -1, and therefore the particles are favored to be fermion-like by this analysis. So these are both confirmations to some extent of the predictions of the jet model. One would like to go even further and be able to see the jets even more clearly. And one other thing that you would like to see is, so part of this model is that the force carriers of this strong force that bind the quarks together that are responsible for this confinement are known as the gluons, because they sort of glue the quarks together. And we know that there should also be the possibility not just to have 2 jet events, but also 3 jet events. And at the sort of lowest order, the way that these 3 jet events happen is that one of the outgoing quarks from this scatter emits a high energy gluon. That itself will have to hadronize into a colorless object or objects. One can calculate in QCD what the strength of this, what the probability to have a radiation like this is as a function of the energies of the particles. So in a simple 2-jet event, we just have E1 and E2. They should be close to equal and in opposite directions. In the 3-jet event, the kinematics is more complicated. We stick with E1 and E2 as the energies of the quarks. And then we introduce E3 as the energy of the gluon. We compute these fractions x sub I for E1, E2, and E3, where x sub I is E sub I. So for example, E1 divided by the incident beam energy. So the center mass energy is 2 times the incident beam energy for a collider of 2 equally energetic beams. You do this calculation, you find that it depends a little bit on alpha sub s, the coupling constant for the strong force. And then also this fraction, x1 squared plus x2 squared over 1 minus x1 times 1 minus x2. So this gives a characteristic distribution for how often you should expect these things given a set of energies. If I tell you what the collision energy is and what the energies of the 2 quark jets are, you should be able to tell me what the probability to radiate a gluon with the remaining energy that's not already accounted for to be. And there's already some interesting physics in this expression. For example, this cross-section basically diverges if x1 approaches 1 or x2 approaches 1. And these are the limits where the gluon is basically parallel to either the quark or anti-quark, or said another way, if x3 goes to 0, right? If that opening angle is small, then we get back to basically the 2-jet configuration, and this cross-section diverges, which you can sort of interpret by saying that if the gluon and the quark are moving in the same direction, it becomes meaningless to distinguish between a 2-jet and a 3-jet event, because the QQG state basically merges into the QQ state. There's no difference to see. And so if you have, you're requiring the individual particles to have some amount of momentum to like make it out of the collision and make it into your detector. And then this frequency with which this happens should increase as a function of the overall center of mass energy, as well as the jets themselves becoming more energetic and therefore easier to identify due to their tighter collimation. So this state is produced with some cross-section at Spear or at Doris. But we've already seen that it's basically difficult to distinguish the jets there, and you have to revert back to this kind of sphericity and angular arguments in order to claim evidence for a jet-like structure. What you would like to do would be able to actually produce tightly collimated events, not only in 2-jet events, but also 3-jet events. That would be a strong indication that the theory involving the gluon is correct. And this is going to be achieved first at Petra, which is an E plus E minus collider, also located at DAISY, which was able to reach more than 30 GeV in the center of mass by the end of the 1970s. So here's an aerial picture of DAISY from later years. I've obscured the name of this other ring here, which is Hera. We'll talk about that later. Totally different kind of experiment. But what we're talking about here is Petra. And Petra was the site of 4 different experiments. There was Tasso, Mark J, Jade, and Pluto experiments. These were all experiments kind of built on the Mark I model, magnetic spectrometers surrounding the interaction point and augmented with various shower counters, particle ID systems, and muon stations in order to aid in the identification of the different particle types. So these experiments will go on to study many different types of physics, not just 3-jet events, but for our current purposes, we're going to talk about that. So this is a picture of one of the experiments sort of representing for the other ones. This is Tasso, which stands for 2-arm spectrometer solenoid. So you have here the beam pipe basically coming out of the picture, surrounded by a cylindrical drift chamber, which is inside of a magnetic field. You see the return yoke for the magnetic field on top and bottom here, augmented with muon chambers at the top and bottom. It's again kind of in the DASP mold where you see this double spectrometer geometry sort of merging into the 4-pi hermetic detector geometry. Here, the spectrometer arms cover only about 40%, 20% of 4-pi, with the central drift chamber having a much better coverage. One thing that may stand out to you here is the aerogel indicated here, which is part of the particle ID system. So what is aerogel and how does it work? Aerogel is an interesting kind of a substance. It's very light. It's mostly made of air, hence the name. You see here a woman's hand holding a piece of aerogel, which is not completely transparent, but very translucent. It's not very massive, but it's pretty strong for its mass. You have here a brick which weighs 2.5 kilograms being held up by a 2-gram piece of aerogel, and it's perfectly rigid enough to hold up this weight despite looking like a wispy cloud. So this is a synthetic material made in a lab. It's ultralight. It's derived from a gel. So a gel is where you have like linked molecules with the voids filled in by liquid. Here, this is linked molecules with the voids filled in with gas. So you start synthesizing it by setting up this matrix in liquid, and then basically the liquid is removed and the gas is flowed in. And if you do this in the correct steps, you can maintain the structure of this gel while removing all the liquid. This results in a solid with extremely low density and extremely low thermal conductivity. For example, I think aerogel is used in spacesuits to help isolate astronauts' bodies from the forbidding lack of atmosphere outside, the extreme temperatures that you experience in space. These can be made from a variety of chemical compounds, but silica aerogels are the most common and the kind that are used in this application of a particle ID system. People have made aerogels out of many different things by now, and the sort of critical property of an aerogel, which makes it desirable for use in a high-energy physics experiment, is that you can achieve indices of refraction with the aerogel that are rather difficult to produce by conventional means. So the basic problem here, we talked about Cherenkov particle ID systems several lectures ago. There we were talking mostly about days where the reactions being studied were lower momentum, maybe hundreds of MeV or like single digits of GeV. Now we're entering the regime where experiments are dealing with tens of GeV in the center of mass, and therefore we have to be able to extend the performance of our particle ID systems up to tens of GeV of momentum. So as the center of mass energies increase, particle ID systems need to use materials with indices of refraction closer to 1, because remember the critical velocity at which particles produce Cherenkov radiation traveling through a substance is related to their to the index of refraction of the material. So as these speeds of the particles get closer and closer to the speed of light, we're building particle ID systems which have indices of refraction closer and closer to 1. In particular, there's a desire for materials with N on the order of, let's say, 1.01 to 1.03. That helps you distinguish the various species of hadrons. Here, most of the time, we're concerned with distinguishing pions, kaons, and protons. And in the energies momentum scale from 1 to 5 GeV, as you can see from the table here, that separation is efficiently achieved for index of refraction of maybe 1.01 to 1.03. Gases, especially gases at atmospheric pressure, usually have indices of refraction which are much closer to 1 than this. And solids like glass have huge indices of refraction, 1.3, 1.5. There's not so many materials which have an index of refraction of 1.02. So aerogels just turn out to be one of the materials that do. The other way that you could arrange for this kind of index of refraction is by using a gas under pressure. The index of refraction of a gas is -1 is proportional to the pressure. So if you want to take, for example, this Freon gas from the table, which has a refractive index at atmospheric pressure of 1.0014, if you want to up that by a factor of 10, so it becomes 1.014 in the range we're talking about, well, that means you need 10 atmospheres of pressure to do it. Now, Freon is already not a very nice gas to work with. It's not good for the environment and not good for people. But if you have to put it under 10 atmospheres of pressure, that means that you need a rather substantial pressure vessel. This is the kind of range of pressure that you might have in like a full propane tank or something like that, right? These heavy gauge steel to hold all that pressure in. And you're talking about a particle ID system where you'd be able to move optical signals out. So you will have to have windows or something in your pressure vessel. Certainly you'll need some kind of ports in order to get your optical signals out. So it's not impossible to do this. Some experiments do this, but it's nice if you can have a material which doesn't require this super high pressure, and aerogel fits the bill. The reason why aerogel has this substantial refractive index, despite its very small density, has to do with its microscopic structure. So you see here at top, this is from a paper by the people who built the aerogel particle ID system for the Tasso experiment. What they've done here is basically crushed the aerogel up and then put it under a transmission electron microscope. And that enables them to image the individual grains of material, which you see as the black dots in this picture. For reference, there's a 0.1 micron distance scale here. So you could fit like dozens or hundreds of those individual little grains into 0.1 microns. So that means the size of the grains is typically on the order of tens of nanometers. That is smaller than the wavelength of visible light, which explains why it has these kind of interesting optical properties. And then those grains are sort of packed into a foam-like structure, basically, where if you picture a foam of soap bubbles, replace the soap bubbles by walls made of these silica grains. That's what it is. So how are these experiments at Petra gonna make the determination if they see the three jet events or not? One of the ways they do it is by defining new event shape variables, sort of by analogy or extension of the sphericity we talked about earlier. And one of those is called aplanarity. So for a hadronic event, one can define a plane for that event by defining the axis of sphericity as before. So that is, I choose one axis such that the momenta of all the particles in the event transverse to that axis is minimized. So that would be my axis of sphericity. And then if I define a second axis such that the sum of the squares of particle momenta out of the plane defined by those two axes is minimized. So in the case of a two-jet event, the one of those axes would be the same axis that we use to compute the sphericity that basically runs along the direction between the two quarks. And then the second one will be in the opposite direction there. And then that would define a plane with both jets basically lying on the plane. In the case of a three-jet event, I could have, and then the aplanarity for this arrangement is measured by taking all the individual particles, measuring their transverse momentum with respect to that plane, and then summing that up and dividing by the sum of all the momenta in the event, again, with this 3/2 normalization factor, just like we had for the sphericity. And it turns out if I try to measure three-jet events, their aplanarity, so in concert with the sphericity, I can use the aplanarity to get myself a sample that's going to be enriched in three-jet events. There basically will be a class of events. If three-jet events are real, there'll be a class of events with a high sphericity, meaning that they don't fit the two-jet description. In this example, the sphericity axis is still pointing along this direction here where my mouse is moving. And then these other two jets, while they add up to go along that direction, the individual particles are actually not traveling along that direction at all. So this event would have a high sphericity. It doesn't look like a two-jet event, but it still has a low aplanarity, meaning that the jets themselves are still more or less collimated. There's not a lot of broadening of the jets out of this plane relative to their PT. And this class of events with high sphericity but low aplanarity is exactly what's predicted by the QQG hypothesis. Moreover, as we saw, the cross-section for this process relative to the two-jet process is a function of the particle energies. And in general, we should expect this class of events to become relatively more common as the energy increases. So one smoking gun would be to make basically a scatter plot of the sphericity versus the aplanarity at a couple of different energies and look for this class of events to emerge with high sphericity but low aplanarity. And indeed, that's what we see here. So we have the distribution of events at two different energies at top 13 to 17 GeV and at bottom 24 to 31 GeV. And you see that this corner here with the low aplanarity and also the low sphericity, sorry, I think I misspoke on the last slide. That's our candidates for the three-jet events. So this is a confirmation, albeit a little hard to understand, of the predictions of the QQG model. What I think was more convincing to a lot of people were plots like this. So these are event displays from the 4 different experiments. So each of them has their own way of doing this, but basically they all have equivalent ways of defining a plane in which to analyze the event and then looking at the distribution of the particles in momentum space projected on that plane. And you see here very clear evidence of a three-jet event. It's hard to really resolve this into two jets. The same thing for this event display from the Mark J detector, where they define angles relative to the thrust axis. This is related to the sphericity with slightly different definition. You see a clear 3-lobe structure to the angular distribution and the momentum here that's highly suggestive of a three-jet event. Pluto experiment making a plot basically identical to the tasso plots on the right-hand side, also showing a clear evidence of a 3-jet event. And finally, you have just a straight up event display from the JADE detector. So this is just a projection of the track directions into the transverse plane, transverse to the beamline in this case, where the 3-jet structure is clearly evident. It's hard to extract quantitative results from event displays, but that doesn't mean that they're not useful. What these experiments did to help convince themselves that the 3-jet events that they were seeing was more than just what could be due to chance or misidentification of particles, et cetera, is they did studies on Monte Carlo samples where they generated random combinations of track directions. And they show that the 3-jet events they show here occur much more often in their data sample than they do in the random pairings. I think it's also interesting to note how these experiments, being fully electronic counter experiments with no visual, there's no film, no photography involved in these experiments at all. And yet, you know, as experimenters, we still tend to fall back on this sort of imaging tradition when the underlying physics becomes hard to parameterize. So it's easy to understand a simple histogram. These variables like sphericity and aplanarity are a little weird to think and reason about, but I think these pictures really show 1,000 words, and they were instrumental in the community accepting that the gluon hypothesis was real, and it will very quickly become an accepted part of the standard model of physics. There's a legacy to these kinds of measurements, which continues even to this day. Those of you who are doing physics looking for like new physics and fully hadronic things where you have a lot of jet mass variables and stuff like that, transverse masses and whatnot. We're sort of working in the tradition of these researchers who are trying to find simple but powerful ways to parameterize the extremely complicated phenomenology of hadronic events in ways that made it possible to extract useful physics information from them. So people will continue to study jet events using these sort of kinematic variables at further colliders. We'll probably look more at plots like this when we're talking about the SPPS, the Tevatron, and eventually the LHC. But it all started here at Petra. So I'm going to finish up now for today. I'm going to post this lecture on the webpage, and I'll send you a notification when that is done. I'm also going to post the second homework set, which I'm sure some of you have been eagerly awaiting. I will see you guys as regularly scheduled for the lecture next Tuesday, the 15th. So talk to you then.